Good evening. My name is Fred Lowe. I'm the director of the National Radio Astronomy Observatory. And welcome everyone to the 46th Annual Jansky Lecture. The lecture series was established to honor Carl Jansky, who in 1932 was the first person to detect cosmic radio waves from the center of a galaxy, actually, thereby founding radio astronomy and providing a new window through which to view the universe by enabling astronomers to study radio waves from astronomical phenomena. At this point, it's a special pleasure to welcome 4 members of the Jansky family to tonight's lecture. Carl Jansky's son, David. Hi, David. And his son, Greg. And Carl Jansky's nephew, Curtis. And his son, Matthew. So welcome. So this year's Carl Jansky public lecture will be presented by Dr. Sandra Weinreb from Caltech and JPL. Sandy received his PhD in electrical engineering from MIT in 1963, so my alma mater as well. While still a graduate student at MIT, he developed the world's first digital autocorrelation spectrometer and used it to place a new upper limit at that time to the deuterium to hydrogen ratio in the galaxy. Perhaps more importantly, working with Al Barrett, Lip Meeks, and J.C. Henry, he detected the OH radical in 1964, I believe in absorption against Cas A. And that was the first radio observation of a molecule in the interstellar space. Before that, as you know about hydrogen, the simplest element, and helium and so on, but a first molecule in the radio. In the optical, people have seen the molecules, radicals as well. Sandy's autocorrelation spectrometer technique is now in use at virtually every major radio observatory and has been crucial in fueling the explosive growth of interstellar molecular spectroscopy in the 60s and 70s. The then new field of interstellar molecular spectroscopy led to the identification of the very important molecular phase of the interstellar medium in our galaxy, or the molecular clouds. And molecular clouds, as astronomers later found out, that's where stars are formed. And as you know, star formation is a very fundamental process in astronomy in understanding the formation of new suns and new planetary systems. And since galaxies are made up of stars, understanding how stars form is basic to understand how galaxies form. So that development of molecular spectroscopy that led to the realization that molecular clouds are important components of galaxy is a very important development in astronomy, and in no small part because of what Sandy has done. As you know, the world's largest ground-based astronomical facility, ALMA, is being built in Chile. It will be finished soon. Early science is going to start at the end of this month. And the reason it's being built because of all that development of molecular spectroscopy and recognition of molecular clouds and so on. And as you may also know, much of the development and the production of many of the key components for ALMA actually takes place very close to here in the NTC building, next door. So Sandy came to NRAO in 1965 to be the head of the electronics division and later assistant director. During his 23 years with the NRAO, he pioneered the use of low-noise, cryogenically cooled solid-state amplifiers in radio astronomy. He was the architect for the electronic systems design for the Very Large Array in New Mexico, and led the group that developed the novel front ends and the data transmission, acquisition, and monitor and control systems for the VLA. And the VLA, since then, has been the most productive ground-based astronomical facility in the world. And next year, it'll be reborn as a new expanded Very Large Array after 10 years of upgrade to replace all its electronics. Since leaving NRAO, Sandy worked at Lockheed Martin Laboratories and then at the University of Massachusetts, where he developed the monolithic microwave integrated circuits, MMIC, which is components in all kinds of devices these days besides radio astronomy, as well as other millimeter wave devices. He has also been a visiting professor at the University of Virginia, and more recently, Sandy, as you know, has been affiliated with Caltech as senior faculty associate and senior principal scientist at the JPL. And he's continued to work on MMIC devices and playing a leading role in the electronics design for a new deep space network tracking array. And just this afternoon, he gave a talk along with a student about forefront LNAs and wideband feeds and so on. In the final analysis, I believe Sandy's distinguished contribution astronomy, or what distinguished Sandy's contribution astronomy, is his ongoing efforts to develop techniques essential to the advance of radio astronomy observations, and very importantly, also responsible for training many, many excellent students over the years in his tradition. And we have the proud example of one of them on our staff. So almost 50 years after his development of first digital correlator, he continues to push the envelope for future radio astronomy instrumentation and facilities. So we're delighted to have a scientist of Sandy's stature for the 2011 Jansky Lectureship. And his lecture tonight is entitled Radio Astronomy from Jansky to the Future, an Engineer's Point of View. But before we start, I'd like to present him with a plaque and a check for his. So, Sandy Weinreb.
Well, thank you for a very nice introduction. Is this working okay? People hear me all right? Well, what I'd like to do tonight is cover the topics that I show up here. I want to start with historical view of radio astronomy and a historical view of my career. I'll then talk about a few of the most fascinating science topics that I find in radio astronomy, and then talk about some of the technology advances that are benefiting radio astronomy, and then a little bit about future recommendations. Now to start with, this is a favorite picture of Carl Jansky with his antenna, and this paragraph here is from the New York Times, which has very brief headlines, and you have to read every word. And I thought this was very well written. It says, mysterious static reported by Carl Jansky held to differ from cosmic ray. Now, a little bit surprised me why it said cosmic ray. Cosmic ray in the 1930s was an important branch of astronomy. Cosmic ray particles. These are subatomic particles that hit the atmosphere, were being discovered, and in fact there was a Nobel Prize in 1936 for cosmic ray discovery. So the New York Times takes note of that. The direction is unchanging. Now that says a lot. Jansky discovered a signal coming from the sky, and by studying how the position of that signal changed as the Earth rotated or as the Earth went around the sun, he determined that the direction was the center of the Milky Way, the galactic center. He first thought that maybe the signal was, well, first he thought it was interference, it was something coming from Earth, but then he found that it was coming from a fixed direction in the sky. And then he realized it wasn't the sun, it was coming from the center of the galaxy. Recorded and tested for more than a year to identify it is from the Earth galaxy. Its intensity is low, only delicate receivable able to register. And then this final sentence, no evidence of interstellar signaling. That is, even in 1932, people were thinking about extraterrestrial civilization. And when a signal like this was discovered, people thought, was it another civilization? So he discovered the first cosmic radio waves by accident, by investigating static associated with transatlantic telephone calls. He worked for the telephone company. Like all good radio astronomers, he wanted to build a bigger dish, bigger telescope. And he wanted to build a 30-meter dish, but as is so much the case with radio astronomy, the funds were not available to do that. What was surprising to me, I have not ever understand exactly why, professional astronomers ignored the discovery, and an amateur named Groth-Reber took up the work. And I'll say a little bit about Groth-Reber in a minute. This is the antenna, which is now at Green Bank, or a copy of it is at Green Bank. Here is Jansky looking at the chart record. That is, there were no computers, of course, in those days. Data came out in this form, a pen marking a chart recorder, sort of like a cardiogram. And the antenna rotated every 20 minutes. And when it pointed in a certain direction, he got a peak of signal. And was studying how that peak changed as the Earth moved that led him to deduct that it was coming from the center of the galaxy. Now this is a favorite diagram of mine. I'm a radio engineer, and I grew up in the days of vacuum tubes. For those of you who have not ever seen a vacuum tube, I happen to have one here. I would pass it around, but it's an heirloom. And, it's of the type shown right here. That is, the signal comes in the antenna, it goes into this vacuum tube. There's a local oscillator to convert down. This is a super heterodyne receiver. But what's very unusual about the receiver was that it was a feedback controlled receiver. The output of the receiver drove a motor which drove this attenuator, which kept the output of the receiver constant. It was a way of achieving wide dynamic range. The problem in the receiver was not noise figure. Even with a triode at 20 megahertz is where he did this. There was enough signal that noise figure wasn't a problem, but dynamic range, linearity, and calibration were the problems. So Jansky referred to his receiver, a reference back to 1928 or so, which then referenced a paper in 1926, which has this diagram in it. Very unique receiver, a good receiver by present day standards. Now this is a photograph of the receiver. I wish I had a better copy of it. This is a rack. This is about 2 feet wide. And for example, that motor-driven attenuator is right here. And some of the tubes and the coils are up here. You can't make them out very well. Now this wasn't the first possible radio astronomy signal. That is, in the 1920s, Milner and Gaimner used a wire antenna 30 miles long to try to detect Mars in the 1 to 6 kilohertz range. You need a long wire to make a good antenna in the kilohertz range. And they did it when Mars was at its closest approach. And the headline here, Mars refuses to answer. They've received nothing. Now, the person who picked up on Jansky's discovery was Grote Reber, who was a remarkable person, as was Jansky. Grote Reber built a 10-meter parabolic reflector. He didn't ask for the money, he paid for it himself. He built it on his own nickel in his backyard in Wheaton, Illinois. He did most of the construction himself. He actually welded the pieces together to make the antenna. And a copy of this antenna is also at Green Bank. He reasoned that higher frequencies would produce stronger signals than at 20 megahertz that Jansky received his signal at. And he had good science reasons to believe that, but he was wrong. And he didn't detect anything at 3,300 megahertz. In 1938, he changed the frequency to 910 megahertz, and he also detected nothing. This guy was persistent. He worked by day for Zenith Radio in Chicago and came home nights and weekends and worked on his antenna and his receivers. Finally, in 1939, he changed to 160 megahertz with a much better receiver, and he detected the Milky Way. He made a map of the Milky Way, which is correct to this day. He then moved to Tasmania to do radio astronomy at very low frequencies. Now, Reber was building a telescope in his backyard. This is a modern day Grote Reber. He is a young man, an amateur radio astronomer from Tunisia, who eventually worked for me at Caltech for 5 years. He was building a radio telescope in his backyard. He had never been to college, never driven a car, never been out of Tunisia, but yet he knew about radio telescopes. He had read about Reber, and he knew the internet. And he contacted me on the internet and started asking questions about building the radio telescope. They were excellent questions. And eventually I started asking him questions and thinking about whether he could be a technician at Caltech. So after several months checking up on him and so forth, he was hired, and he was my right hand for 5 years. I miss him very much. Eventually, the visa situation caught up with him. He could not get a visa unless he became an undergraduate student. He's now an undergraduate student at Arizona State University. Now, this is my career in one view graph. Sort of running down the line. Born in New York City, born of parents who were immigrants from Poland, came over in 1920. I somehow got into radio, got interested in building crystal radios, one-tube radios. Did that as a child. Eventually learned to fix radios, moved to Atlanta, Georgia, fixed TVs, cars, and plucked chickens. That's a true story. I worked for a radio shop that had a live chicken market in the same store. So when we weren't busy fixing radios and TVs, we sold chickens and cleaned the chickens. I eventually got into MIT. I've got a view graph about that, say a little bit more about that. I received the Most Outstanding E-Student Award in 1958. That was amazing because I barely got into MIT. I'll talk about that. 1957, I was married, have 2 children that are grown adults here today, sitting in the first row, and 2 grandchildren. here, Brody and Toby. I went to graduate school at MIT. I'll talk some about my PhD work. Fred gave me a nice introduction to what I did for my PhD thesis. I then started work at NRAO, worked in Green Bank for 3 years, lived in Green Bank for 3 years. There were very pleasant time I was there. I'm looking forward to going back tomorrow to visit Green Bank. Eventually, I decided, did I want to spend the rest of my life at NRAO? Was this where I would retire? And I decided, no, I wanted to do something else. And I went to work for Martin Marietta in Columbia, Maryland, learned about designing monolithic integrated circuits. That was closed, that research lab closed when Lockheed bought them. I then went to the University of Massachusetts where I did some teaching and had some graduate students. And since 1999, I've been in Pasadena, California, where I worked for JPL, worked on the Deep Space Network, worked on low noise amplifiers, and I think my prime purpose in life right now is mentoring students, is teaching students. Okay, there's Sandy, age 13, at a radio shop in Miami, Florida. There I am with my soldering gun, fixing a radio. Those were the good old days. Now there's my son in 1976, sitting here on the first row, working in the lab at Berkeley. I did a sabbatical leave at Berkeley, and he was working on something here. When he was 12, I gave him a birthday present of a Heathkit microprocessor trainer kit. It cost $200, which was an expensive birthday present in those days. Best investment I ever made. He learned about microprocessors. He went to MIT, but he claims he learned more from the Heathkit microprocessor kit in his years at MIT. He eventually started and still runs GW Instruments, a company selling data acquisition equipment. This is the website. Today in the lab here, I saw some of Glenn's equipment still there. Apple computer and a data acquisition system that Glenn had built 30 years ago. Also have a daughter, Ellen, who's sitting here in the first row. Ellen is an economist. She was in the Peace Corps in Cameroon. Here she is teaching coffee economics to the coffee farmers in 1991. Ellen now runs a recruiting company for social responsible business, and this is her website address. She's married with these 2 great grandkids, and they live in Berkeley, California. Now, back to Sandy Weinreb. Well, this is the report card that got me into MIT. And if you look at the grades, this was the senior year report card. I was a solid B student, all semesters, all subjects, except military. I got an A in military. I was a good marcher, and I cleaned my rifle very well. I somehow got into MIT, and these were my buddies. I think it was peer pressure that kept me as a B student, and these were the B students who were the peer pressure. This is 20 years later. This is the high school 20th anniversary reunion. And what is remarkable about this picture is this car. It belongs to this fellow. It's a 1954 Chevrolet. And when he was 16 years old, he's 36 here, when he was 16 years old, his parents gave him the new Chevrolet as a birthday present. Well, that was a bad mistake. Don't do that with with your kids. He was caught on Peachtree Street racing the 54 Chevrolet. His license was taken away, and then he was caught racing on Peachtree Street with no license. And so when I came home from MIT the first Christmas, he was in the state prison farm for driving without a license. And he straightened out, though. He said they were mean in there, and he didn't want to go back. He became a veterinarian and became very well off. He could afford to buy this car, and he had several other cars. Came to the reunion in this car. Now, how did I get into radio astronomy? Well, my junior year at MIT, I wanted to look for a summer job, and I went through the phone book and I called up every company under electronics and physicists. Luckily, I included physicists, and there were 4 companies in the phone book under physicists. One of it was called Ewan Knight Corporation. It was run by this fellow, Doc Ewan. He was the discoverer of the 21-centimeter hydrogen line, one of the key discoveries of radio astronomy. And he got me enthusiastic. I worked for him that summer and continued to work for him in other summers. This was an interesting thing. His funding proposal to detect the hydrogen line, it was a total of $500. He did it at Harvard. He pointed an antenna out the window and detected the hydrogen line. Things were easy in those days. It was easier to make a fantastic discovery because you're getting in on the ground floor. Now, as Fred mentioned, one of my contributions to radio astronomy was the digital correlator. This was the first digital correlator. It cost $19,000, which was a lot of money in those days, but the capability is measured on this chart, and it was very expensive by present-day standards. That is, if you measure the cost per operation per second, this has gone down by about 100 million since I built this first correlator. And this is a chip which does enormously more than this whole 3 racks of equipment. But I was very proud of this correlator, and the story I want to tell is I had a thesis committee which consisted of Alan Barrett, who's a well-known radio astronomer many of you have heard of, and Jerry Wiesner, who, while he was my thesis supervisor, became President Kennedy's advisor. And actually, when I made some measurements here in Green Bank, on the way back to Cambridge, I went to Washington and reported to him in the executive office building of the White House. But there was a third member of the committee that I want to mention. And every time I would go see him, I'd visit his office and go in his office, and he's playing with his hi-fi system. And he had all kinds of speakers in his office. And I thought to myself, gee, I'm working on something like radio astronomy, something very esoteric. And here this professor is there playing with his hi-fi system. He's not going anywhere. Well, his name was Amar Bose. He had something in that hi-fi system. He used to tell me, you can make the perfect speaker, the perfect amplifier, but the room is what changes the sound. And you've got to design a speaker system that takes care of the room acoustics. And I think that's what he did. But he recently gave the majority of his company, he's a billionaire, the company's worth over $1 billion, he gave it to MIT. So I was wrong about my judgment. Now, the discovery of OH, the first molecular line in radio astronomy. Well, this turned me into a radio astronomer. This line was detected in the first 20 minutes of observing. I had spent about 6 months at Green Bank looking for the deuterium line. I had a negative result. That is, we did not detect the deuterium line, even though the Russians had said they had detected it, and it turned out they were wrong. But we looked for hydroxyl, the OH line, and very quickly detected it. In 20 minutes, we received this dip, which was exactly where Alan Barrett said it would be. As Fred mentioned, molecular lines are all over the place now. This is a spectra up in the millimeter range, but each one of these lines comes from a molecule. So we're able to study chemistry in distant regions by measuring the strengths of these lines. Each one comes from a different molecule. And it's one of the strong areas of radio astronomy is molecular spectroscopy. All right, getting back to NRAO, there were some key decisions in those days. They weren't necessarily my decisions. They were Dave Heesian and Hayne Bottom, myself, decided on some of these things with plenty of good advice. But you might wonder how the VLA got the way it is. And it did start out that way. As I'll show in the next slide, we started with antennas on rubber tires, and that didn't work very well. We started with antennas connected with coaxial cable, which was very expensive, very limiting in performance. We had much fewer front ends, frequency bands, in the initial proposal of the VLA. We used something called parametric amplifiers, which were deadly, very difficult to maintain and build. And we used cable delays initially. We eventually went to digital delays. So this is what an antenna on rubber tires looks like. And you imagine that bumps around on a roadway. You always wonder if the antenna is going to keel over. The VLA moves on rails. And Hayne Bottom was a buff of rails, and we were a little prejudiced or worried about he was too prejudiced about trains, but he was right. This was the way to move the VLA antennas. Okay, what did I do when I left NRAO for 7 years? Left radio astronomy. I had worked on the VLA, the Very Large Array, at NRAO, so went to Martin Marietta and they thought of Very Small Array. This is actually an array of antennas. On the end of each one of these is a little millimeter wave dipole antenna. So this is sort of the same principle as the VLA, an array of antennas with amplifiers and combiners, but it all fits on a postage stamp. And that's what I worked on for 3 or 4 years. These little antennas went into a missile seeker. That is, it looks like this. It's a radar transceiver that goes in the nose of a missile. And this is some of the other stuff that I worked on at Martin Marietta. And while at Martin Marietta, my good friend Bill Howard, who's in the audience here today, got me a position on the Army Science Board. I think Bill was working for CIA at that time. Army, okay. And thanks, Bill, for the invitation. I did it for, I think, 2 days. I decided I just didn't know enough about the Army. I didn't feel qualified to be on the Army Science Board. But it was an interesting 2 days. One of the days was down at, I think it was Fort Gordon, and we were to drive tanks. That is, I was down in here driving this tank. And the trouble was that all the other members of the science board were driving tanks, and none of us knew how to drive tanks. They just put us in a field. We were roaring around in our tanks and worried that we would have a crash. There was a soldier up here who could take control, I guess, if he saw that about to happen. But anyway, I had fun there for a while. Now, coming back to radio astronomy, what do I consider the most interesting topics? The first is the cosmic background. Then I'll talk about pulsars and about SETI, the search for extraterrestrial intelligence. Discovery of the cosmic background. Explain a little bit to the audience what this is. If your eyes could see radio waves, the sky would not be dark at night. If you walked outside, you would see a dim glow to the sky. And that's the cosmic background, we call it. The whole sky radiates. And it was hard to discover because the Earth also radiates. In numbers, the Earth radiates at 300 Kelvin. The sky is at 3 Kelvin. It's 100 times weaker than the Earth. So if a little bit of Earth radiation leaks into the antenna, you are fooled in thinking that that's where the noise is coming from. These guys did it right. I remember coming to NRAO around that time, and there was mostly skepticism from the radio astronomers here. They thought they were seeing some of that 300 Kelvin leaking into the antenna. What I remember thinking about it, well, it's just one number. You measure the temperature of the cosmic background, maybe it's 4 Kelvin, maybe it's 3 Kelvin, but it's not going to tell you much about the universe because it's in information theory, you've only gotten one number. How wrong I was, we all were. I like this description. Discovery of the cosmic background radiation changed forever the nature of cosmology from a subject that had many elements in common with theology to a fantastically exciting empirical study of the origins and evolution of things that populate the physical universe. That's become more and more true. The cosmic background, the study of it has told us more and more about the origins and composition of the universe. The one number, well, if you start to remove the average of the cosmic background and start looking, you unpeel the onion and start looking at the variation of the cosmic background as you point the antenna at different spaces, you get a picture like this. And that has tremendous interpretation, which I can't begin to tell you how it's interpreted, but this is the interpretation that, first of all, most of the universe we do not see. 74% is dark energy, what's called dark energy, 22% is dark matter. And everything we see, all the stars and galaxies, only about 4% of the universe. That inference comes out of the study of the cosmic background. So here is sort of a way of looking at this. We're out here now looking back at the origin of the universe. The cosmic background radiation occurred some 400,000 years after the Big Bang. And this was another thing. This confirms or gives a lot of credence to the Big Bang theory of the universe and tells us the universe is 13.7 billion years old. And people believe in that last decimal point that it really is 13.7 billion years old. Another fascinating observation in radio astronomy is pulsars. These are objects in the sky that go beep, 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 beep. They're not coming from another civilization. but they beep. And some of the beeps are fantastically short. They're only a nanosecond, a billionth of a second long. That is extremely short in terms of time of travel of light. It's only a foot or so. And the way I like to think about this pulsar is the time history of it, the chronology of what's called the Crab pulsar. In the year 5750 BC, a star, what is now known as the Crab Nebula, collapsed to form a bright flash in the sky. The flash, it took over 6,000 years for the flash to reach the Earth. But both the Chinese and Arabian astronomers noted it. They could say where it was relative to other stars, and it was something visible even in the daytime. Another several hundred years went by when the telescope was invented, and Messier discovered the supernova remnant. He sees the nebula that was the original exploding star. A scientist at Caltech named Zwicky predicted the existence of neutron stars, and eventually a pulsar was discovered from the same supernova. That is, the supernova gave rise to a pulsar. There was a Nobel Prize in Physics given for the pulsar discovery in Jewish 1974, not this particular pulsar, but other pulsars. So we see a pulse that comes here, and it started in 5750 BC. Now, the other topic which I find fascinating in radio astronomy is the search for extraterrestrial life. And here we are, in the first 5 billion years of the Earth, we did not have the technology to detect a signal if it reached the Earth. It's only in the past 100 years or so that we have this technology. And it's only in the past several years that we've detected planets around other stars. And one of the most exciting NASA space experiments is called Kepler. And Kepler is a spacecraft with an antenna in it. And it stares at 1 square degree of sky for 4 or 5 years. It will just look at that 1 square degree. There's about 100,000 stars within the square degree, and it looks for time variations from the light from those stars, when a planet moves in front of the star, or whether the star wobbles a little bit due to pull of the planet. And the promise is that it will detect 50 Earth-like planets by 2012. I think right now I haven't heard any announcement of an Earth-like planet, but they've got another year to go. And so what is the next step? Well, I think radio astronomers will search those regions where there's Earth-like planets to see if there are any signals. The chances of detecting a signal are very small. And this is an attempt to summarize the situation. The signal depends, what are they transmitting? Are they just having television transmissions and radars similar to what exists on Earth, or are they actually trying to beacon? Are they signaled out the Earth and trying to send us a signal, in this case with 1 kilowatt transmitter, in this case with a megawatt transmitter? And what's shown here is the number of stars which might be detected with the present day technology. So in other words, if there's no beacon, by rights we should not be able to detect any extraterrestrial civilization. With something called the SKA, the Future Square Kilometer Array, who knows when it will be built, but sometime in the next couple of decades, that greatly increases the probability of detecting another civilization. It's still very low. That is, this means that with a 1 kilowatt beacon, there's 2,500 stars. But how many of those stars? 2,500 stars, and only about 1 in 2,000 may have an Earth-like planet. So there may be only one Earth-like planet. And then is that planet at the right time to have technology? So chances are very small, unless there's really beacons, whether there's civilizations out there that are really intending to single out the Earth and send us a signal, in which case there's some chance. Okay, now this is a little game that was played in Green Bank by Frank Drake, an astronomer who was at Green Bank at the time, one of the first people to look for extraterrestrial signals. And suppose we receive this sequence of ones and zeros. Now, a one may be a beep. You know, it may go beep, 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 and then no beeps. And so you get ones and zeros. If we receive this, how could we interpret the message? On the science fiction movies, everybody speaks English. Avoid this question. But if you just receive a binary message, can you make any sense out of it? Now, nobody solved the problem when he gave it to us in Green Bank, but the key is there's 551 ones and zeros. Now, that's a key clue. 551 is the product of two prime numbers. It's 19 times 29. A prime number is a prime number no matter where you are in the universe. It's a mathematical concept. So any civilization intelligent enough to build transmitters would know about prime numbers. And so if you arrange the ones and zeros and color the ones black, you draw this picture. And you can put a little symbol at the bottom of the picture. So you teach the language. You teach the symbol that means human being. And there was other information about the Earth supposedly in this, but it's just an example. You would send many more bits than this. So it would be possible to communicate to another civilization. Now, engineering developments applied to radio astronomy in the past 50 years. Well, I've already spoken about digital correlators. I'm going to tell you a little bit about low noise amplifiers, going from parametric amplifiers to transistors. Another key development for radio astronomy has been optical fibers. Our VLA antennas, many signals in radio astronomy, even the signal from the GBT to the Jansky building is carried on optical fibers. And the last point is chip integration of receivers, making receivers less and less expensive by using integrated circuit techniques. This is a parametric amplifier. It is expensive, bulky, unstable, unreliable. When we proposed the VLA, this is what we had. It was going to have 4 parametric amplifiers on each telescope. What we eventually built were transistor low noise amplifiers, which are tiny chips or discrete transistors. Much less expensive. They're stable, reliable. They do all things good things. This is an example of some low noise amplifiers. Here's a chip again. This is just showing the noise as a function of temperature. They work at cryogenic temperatures. They get much more sensitive. In radio astronomy, we cryogenically cool the low noise amplifiers in order to get that sensitivity. This is what a chip looks like if you have a very high-powered microscope. The transistor is actually this tiny spot here, and there's multiple layers of interconnects above the transistor. There's like a printed circuit board with many layers built into the chip. So you can build very complicated circuits just within the chip. Now this sort of shows the packaging technology, the trends in packaging technology. The first part of this, these two are from Matt Morgan's thesis. Matt Morgan worked at Caltech and now works here now, making a multi-chip MMIC module. That is, in the 1990s, we built receivers by screwing together blocks. This might be a filter, an amplifier, a coupler. That same function could be performed by MMICs within a little module, and Matt demonstrated that. We're headed towards having the whole module multi-function MMICs. That is, where one chip does amplification, mixing, A to D conversion, many operations within the same chip. And where I hope we're headed, I don't know if it would be 10 years from now or more, is the multi-pixel wafer array, where we have many receivers built in the form of a semiconductor or superconductor wafer. It's the radio equivalent of the photographic plate. Most radio astronomy has been 1 pixel at a time. Optical astronomers have photographic plates. They have CCD arrays. They look at a whole image at a time. And that's the direction we're moving in radio astronomy with arrays, and we need to be able to build millions of receivers at a low cost. I'd like to talk a bit about the evolution of the VLA. This is how the VLA started, how it was proposed based on the Green Bank interferometer, 2 frequencies, narrow bandwidth. This had much less area. This is the VLA as it has stood for the past 30 years or so. The EVLA greatly expands on that, expands the frequency range, the same total area. Greater bandwidth helps the survey speed. Where I hope NRAO is headed into something that's either called the SKA High or the North American Array. What will happen to the VLA, say, 15 years from now? What is the future of the VLA? Will it eventually be closed down and replaced by some instrument at some other wavelength, or by some international SKA project? The VLA site is unique. The sites that are being investigated for the SKA are low altitude sites and would not be good for the high frequency range. What is natural is the SKA expand into a larger number of smaller antennas. Smaller antennas increases the survey speed and decreases the cost of the array. Something like 415-meter antennas, a cost goal of $300 million. It has 5 times the area of the VLA. It has much greater bandwidth, 400 times the survey speed of the VLA. So we're very proud of the EVLA. It's a great instrument for the next 15 years, but we should start thinking about the next step, about doing some of the development work that makes this cost believable. That is both in the antennas and the electronics. We need planning to do that, and I hope that will happen over the next 10 years or so. feasibility, there's one thing that I put on here that may have struck you. There's one receiver. That is, to cover 8 to 50 gigahertz, I believe we can do that with one feed and one low noise amplifier. That greatly reduces the cost of the VLA. The present VLA, I think, is, I don't know, it's 8 or 10 receivers to cover 1 to 50 gigahertz, and it's of the order of $1 million a receiver. If we have 400 antennas, we're not going to do it for $300 million. So one way is to reduce the number of receivers by building wide bandwidth receivers, and currently we're working on that at Caltech. This is what a feed might look like that would cover 8 to 50 gigahertz. This is just showing that the patterns do not change with frequency. You need that to make an efficient feed for that wide a bandwidth. The low noise amplifier we're also working on. There's a student here, Ahmed, back there, who's worked both on the feed and the low noise amplifier. This is actually the room temperature noise, but we think when the amplifier is cooled, we can get about 15 Kelvin of noise from 8 to 50 gigahertz. So there's some initial steps in this direction, and I think that needs to be followed through with much more work. Now this is getting back to this, the radio photographic plate. This is a cross-section view of a millimeter wave receiver made in layers. It might be a superconducting layer that has the antennas and superconducting junctions that make mixers, and then a layer of semiconductor IF amplifiers, and then photonic layer. So it all comes out in a fiber bundle. So at the focal point of the telescope, you have this device, and it just comes out in a bundle of fiber. Some recommendations. Some of these may be obvious. Some of them are in the NRAO long-range plan. There is the mid-frequency SKA being developed internationally. The United States has chosen not to build the mid-frequency SKA, not to participate in the construction, but we can participate in the development. In places where NRAO has particular expertise or could advance the development, they should do that. They should try to help our international partners with this work. I've already mentioned the North American array. I think NRAO should work on development towards the next stage of the VLA. There should be a robust technology development plan at NRAO. I see this in the long-range plan. It's good to see that. Finally, this is a dream that I've had since coming to JPL. JPL and NASA needs large antennas. Like the VLA, they actually used the VLA for the flyby of Neptune Voyager spacecraft. But NASA and NSF just don't get together on this. NASA builds its own telescopes, NSF builds its own telescopes. I think the country could save a lot of money if they combine. NASA doesn't necessarily need these large telescopes that much of the time. They need it for critical events, when a spacecraft is landing on Mars or some other planet, or something goes wrong with the spacecraft. Then they need a lot of collecting area. And the final view graph, it just shows the current NASA capability, deep space network, This is the data rate in bits per second as a function of distance from the Earth. And this, for example, is the distance of Mars. And you never see a TV image from Mars. And it's not that we can't send the TV camera there. They're very small. We could certainly do that. But we can't get the data back because we don't have enough transmission capability. There isn't enough power in the spacecraft. There isn't enough collecting area on Earth. If we built something like the SKA, we could get video images from Mars. And what's even more important, the spacecraft could be a lot smaller. NASA could actually save money if they built more facility. If they put a few $1 billion into Earth facility, the spacecraft could be smaller and would be much less expensive. So that concludes my talk. Thank you very much. Be glad to take any questions.
Yes, Skip?
You were talking about working for broadband feeds and low noise amplifiers as cursory developments for something like SKA high. As father of the digital electronic correlator, could you comment on how you can reduce the cost of the signal processing, something like SKA high, which in today's dollars would probably eat up more than a $300 million budget?
I have a friend at JPL who has the answer to that. His name is Larry D'Addario. Maybe he has. Who? Larry D'Addario. It's not, those digital correlators get less and less expensive as logic develops, as Moore's law goes on, cheaper computers. But Larry has a different architecture for the processing that he claims, for example, the correlator would require 100 times less power. And Larry is usually right. And so there are some developments in that direction. I can't explain it, but talk to Larry. Any other questions?
Yes.
Coming from a non-engineer background, could you explain perhaps some of the obstacles in developing such a blind ANSI?
Explain
Some of the obstacles in developing
obstacles.
Obstacles.
Well, the first obstacle is that basically most antennas, for a given size, the beam width gets sharper as the frequency goes up. So if you take a horn antenna, you take a dish antenna, the beam width is getting sharper and sharper as frequency goes up. For a feed, for a parabolic reflector, you want to have a constant beam width. So that's the basic obstacle, is you have to design a feed that as frequency goes up, the beam does not get sharper. And it is possible to do that. It's been done by computer optimization techniques. But that's the basic problem.
Other questions?
Have you seen the rubber-tired Alma antenna transporter? What
No.
do you think of that?
Is there such a thing?
Yeah.
Well, the antenna transporter, okay.
Yeah.
Right, all right, there's no track,
No.
Alma?
that's
Yeah,
right.
okay.
They're small.
It's what?
They're small. The antennas.
They're small. Yeah, okay. 12-meter antenna, yeah. No, I bet it's fun to move it, those rubber tires. Yeah.
Yes, Bob.
Bob?
Sandy, what's the view from within JPL regarding the Deep Space Network? Is NASA planning seriously to deal with the enhanced obsolescence of the current DSN? Are they planning for backup in case of a deep space mission that's suddenly jeopardized because of major failures? We've had this conversation before. We're puzzled that NASA's.
Yes, I think it's somewhat, it's a chicken and egg thing. Nobody proposes a space mission that needs more than the present space network. If they did, they may have to pay for it. And so all spacecraft, they have enough power to deal with usually the 34-meter antennas. That is, NASA has some 70-meter antennas that are getting obsolete, and they're considered risky. But the present plan is to build more 34-meter antennas, a few more. The investment in an array is an infrastructure thing that would help NASA over like a 30-year period, as long as you use the array. But they don't look that far ahead. They're worried about next year's budget and getting by. And so that's the situation. I hope something can be done about that, and maybe some collaboration with radio astronomy.
Yeah, Bill?
Yeah.
Sandy, could you say something about the BLA hollow waveguide? I've just always been amazed by that achievement, and also struck by the fact that optical fiber came along so quickly to kind of make it obsolete.
Yeah. Well, it was, I just was talking to Dave Heeshan yesterday about this. It was one of the riskiest decisions that we made on the BLA to use the hollow waveguide. It's enormously better than the coaxial cable. And I'm so glad we did it. But it was risky. That waveguide has to be extremely straight. It has to be waterproof. There's all kinds of things that could have gone wrong with it. But it enabled us to go from 10 megahertz bandwidth to 50 megahertz bandwidth. And it's much more reliable. The coaxial cable system had to have a repeater buried in the ground every few kilometers. So the waveguide was something worked on by the telephone companies of the world, Bell Labs and telephone companies in Japan. We bought the waveguide from Japan. We had a lot of good dealings with telephone companies in Japan to get the waveguide, get it installed. So it was certainly the right decision for the time. There was no such thing as optical fiber. It worked for 30 years, so it was a good decision. Anybody else?
Yes.
How is the proliferation of wireless technology impacting radio astronomy?
Helping it enormously. That is, you may be thinking of the wireless interference to radio astronomy. Of course, that is a problem. But all these less expensive electronics is an offshoot of the wireless industry. In the early days of radio astronomy, we rode on the defense developments in defense electronics, radar and so forth, developed for defense purposes. But nowadays, it's more chip technology that comes out of the wireless industry. And when we start needing thousands to millions of receivers, we'll be copying the cell phone. I mean, think of your cell phone has something like 10 transceivers in it, and it doesn't cost that much. And that's the direction we need to move into in radio astronomy.
Other questions? If not, let's thank Sandy Weinreb again. Thank you. That was great. Thank you very much.